Hello guys, welcome to this Power Up series for the super fast revision of chemistry. In this series, we discuss the important concepts of some of the most important chapters, right? And today, the chapters we are going to discuss are gaseous state, thermodynamics, and chemical equilibrium. So if you have missed yesterday's video, please go over to a YouTube channel. You will find there one video on chemistry wherein I discussed the important concepts of the three chapters yesterday I took up. Those were mole concept, solutions, and the other chapter was atomic structure. Okay, and today's topics will be these. You guys know that thermodynamics and equilibrium, these are very important chapters. And as always, what we will do, I'll show you the question. If you're watching this video, you can pause this, solve the question yourself and check the solution, or if you have doubts in the concept, then you can watch the entire concept here also itself, right? So starting with the first question, I'll take first question from gaseous state. You can see here that an open vessel at 27 degrees Celsius is heated until 2/5 of the air has escaped from the vessel. Okay, so in gaseous state, many numericals are based upon the ideal gas equation, right? Now, if you are comfortable with solving numericals, then you don't have to mug up all the formulas. You should just know how to derive the requisite formula using the ideal gas equation, as I will do in this question, right? So basically PV is equal to nRT, right? PV is equal to nRT. Now read this question carefully. An open vessel, right, at 27 degrees Celsius has been heated until 2/5 of the air escapes. One more tip, if they talk about in the fraction, okay, if they talk about in the fraction like in this question, so we will take the initial amount of air as 1, that will be sufficient. Initial amount of the air as 1, and the final amount of the air, the 2/5 has escaped from the vessel. So 2/5 will have escaped, and this will be 3/5. So we can say initial number of moles of the gas was 1 and the final number of moles is this 3/5. Okay. Now assuming that the volume of the vessel remains constant, the temperature at which the vessel has been heated. Okay. So R is constant in this equation. Now please focus, because now I will show you how to derive the requisite formula for your question, right? So in ideal gas equation, R is constant anyway, right? Here the volume of the vessel is also constant. So remove this, volume of the vessel is also constant, right? Pressure will also be constant because the vessel is open, right? If the vessel is open, the pressure of the gas will be equal to the external pressure, right? It's very easy. So pressure is constant, volume is constant, and R is anyway constant. So can I write, guys, that PV divided by R is equal to NT is equal to constant, right? Can I say that? Okay. So PV, R, all these are constant, and so of course NT will also be constant because it is equal to that, right? And then from here, for the two states of the gas, I can write N1 T1 is equal to N2 T2. Am I correct? So from here NT is constant, N1 T1 is equal to N2 T2. Now you just have to substitute the given values here. Okay, let us do that. So N1, I have taken 1, the most simple way of doing these type of questions. Initial temperature is 27 degrees Celsius. Now this is another point where many of you make mistakes. You do not convert the temperature to Kelvin. You directly substitute it in degrees Celsius. Please do not do that, right? Please remember the temperature difference in Kelvin and Celsius scale, that remains the same. So if they're asking about temperature difference, then you can use, okay, the same value. But if it is about temperature, then always convert it to Kelvin. So 27 degrees Celsius, it will be converted to Kelvin, equal to final number of moles is 3/5 because 2/5 has escaped from the vessel. So final number of moles of the gas will be 3/5 multiplied by final temperature that we have to calculate. So of course the final temperature, it will come out to be 500, and always remember the answer will come out in Kelvin, that is SI unit. So this is 500 Kelvin, that is the correct answer. Okay, so we will discuss some questions, and I'll also tell you, I'll also revise the important concept with these questions. Like this question, if Z is a compressibility factor, what is the van der Waals equation at low pressure? Okay, so let us first discuss van der Waals equation. Okay, so you guys know that van der Waals equation is this: P plus A n square by V square, V minus NB is equal to nRT. All right. Now please remember that P pressure, V volume, n number of moles, R universal gas constant, T temperature. These things you know already. But here there are two terms that were not there in ideal gas equation, which is A and B. So small a and small b, these are van der Waals constants. A is a measure of the attractive force of the gas particles. Greater the value of A, greater will be the magnitude of attractive forces. And B is a measure of the effective volume, excluded volume, right? Effective volume occupied by the 1 mole of gas particles, okay? So this is our van der Waals equation. Now we can take n as 1, right? Number of moles we can take as 1. So van der Waals equation reduces to P plus A by V square, V minus B is equal to RT, okay? Now this van der Waals equation can be converted into several forms depending upon the conditions of temperature and pressure. For example, if you are considering very low pressure and very high temperature, right? So if the pressure is very low, particles, if the pressure is very low, what will happen? Volume will be very high, right? Volume will be very high, particles will be very away from each other, and temperature is also high. That means there is no attractive forces. So please remember that at low pressure and high temperature, when the real gas behaves almost like an ideal gas, right? The behavior is similar. So what will happen? This term will become 0 and this term will also become 0. That means PV will be approximately equal to RT. Yes, mathematically we have shown that the real gas is behaving almost ideally, okay? Now at intermediate pressure, at low to intermediate pressure, what happens? When the attractive forces are dominating, when the attractive forces are dominating, so of course guys, now you cannot ignore A by V square, you cannot ignore the attractive forces, right? See, at very low pressure there is no attractive force, but as you increase the pressure by decreasing volume maybe, then what happens? Particles come closer. Now as particles come closer, attractive force between them increases, right? So now A is no longer negligible, but B can be neglected, right? Because still the volume is not very low, right? The pressure is not very high. So B I'll ignore and I'll write it as P plus A by V square, V minus 0. This I've ignored, right? Is RT. Now you can simplify this expression. So this will be PV plus A by V is equal to RT. Alright. Now you can divide this entire expression by RT. Okay. Right. You can divide this entire expression by RT. So that gives us PV by RT plus A by RTV is equal to 1. And you guys know Z is nothing but PV is equal to RT, right? Compression factor or compressibility factor Z is PV by RT. So Z plus A by RTV is equal to 1, or Z is equal to 1 minus A by RTV. Okay. So this is the expression of compressibility factor at low pressure, right? Okay. Z is equal to 1 minus A by RTV. At very high pressure, the expression becomes Z is equal to 1 plus PV by RT. Why? Because in that case, now you ignore A by V square and you consider B, right? So in that case, PV minus B is equal to RT. Same way, now you can write it as PV minus PV RT, right? Divided by RT and substitute PV by RT by Z, okay? So one thing you should remember here is that for an ideal gas, the compressibility factor is always 1, right? Why? Because for 1 mole of an ideal gas, PV is always equal to RT. So Z will always be equal to 1, which is PV by RT. So the value, so we have learned so much in these last few minutes. So the expression of compressibility factor at low pressure is this, at high pressure is this, and for an ideal gas, it is this, right? Moving to the next question, this one. Again a question based upon ideal gas equation actually, right? Some might call it based upon Boyle's law, but you can definitely do this question using ideal gas equation itself, right? So let us look at the question. A spherical balloon of radius 3 centimeter containing helium gas has a pressure of 48 into 10 to minus 3 bar at the same temperature. So temperature is constant. The pressure of a spherical balloon of radius 12 centimeter containing the same amount of gas, right? So again, let us look at PV is equal to nRT. Out of the two given cases, what parameters are constant, right? So first thing, temperature is constant, temperature is constant, and the same amount of gas, that is also constant, R is also constant. So basically here PV, which is equal to nRT, is a constant. Alright, so I hope you guys can figure that out from the question itself. Temperature and pressure, temperature and number of moles, these two parameters are constant, right? So N and T, they are constant, so of course PV will be constant. Now if PV is constant, so P1 V1 is equal to definitely P2 V2, right? P1 V1 will be definitely equal to P2 V2. Now for the first balloon, the pressure is 48 into 10 raised to the power minus 3 bar, right? For the first balloon, pressure will be 48 into 10 to the minus 3 bar. Volume will be 4 pi by 3 into 3 centimeter, right? Cube. That will be the volume of the balloon. Now at the same temperature, what will be the pressure? Okay, so pressure is something we have to calculate. What will be the volume? Again, because the balloon is spherical, so it will be 4 pi by 3, and this time the radius of the balloon is 12 centimeter, right? So that is to the power cube. So this will be cancelled out, okay, and now you can calculate what will be the pressure. So pressure will be 48 into 10 raised to the power minus 3. Alright, this is the pressure. 4 pi by 3 has cancelled out, so this is 3 cube, right, which is 27, and this thing divided by, right? Alright, so now I think you do the calculation. Remember, the answer will be some number into 10 raised to the power minus 6 bar, okay? So it will be 3 by 4, so that is 0.75 into 10 to the minus 3, or 750 into 10 raised to the power minus 6 bar. So you can calculate the question from here, answer from here. Moving to the next question, this one, another type of question that are very common are based upon the molecular speeds, right? Okay, so these statistical speeds, or these molecular speeds of gas particles, how do we define them? So you guys know that molecular speeds are of 3 types, right? Let us quickly see their formulas. So first is most probable speed. What is the formula of the most probable speed? We can say most probable speed is under root 2 RT by m, right? Under root 2 RT by m. Most probable speed by definition is the speed possessed by the maximum fraction of molecules. Then you have average speed, right? Average speed, what is it equal to? Average speed is under root 8 RT by pi m. So this will be a number between 2 and 3, right? Okay, and finally the RMS speed, on which the kinetic energy of the gas depends, right? So this is root mean square speed, RMS speed we call it in short. So RMS speed is nothing but under root 3 RT divided by m, right? So these are the 3 statistical speeds that we discuss for the gaseous particles. Now please remember that most probable has the minimum value and RMS speed has the maximum value for a given gas at a given temperature. Alright, so questions based on these formulas are very common in JEE. For example, this question, what is the ratio of RMS speed of methane at 27 and sulfur dioxide at 927, okay? So let us first make the ratio. RMS speed is under root 3 RT by m, right? So please remember, when you are making the ratio, 3R will cancel because it is a constant. 3R will cancel whenever you make the ratio of two things, constants cancel, right? So how will I write it? The RMS speed of methane divided by the RMS speed of sulfur dioxide, okay? Now it will be very easy, it will be proportional to the square root of the ratio of temperature and molar mass, right? So temperature of methane, which is given to be 300, divided by molar mass of methane, which is 16, right? So please remember that although in this formula you should substitute the molar mass in kilogram, right, in SI unit, but because we are writing the ratio, so the 1000 factor will cancel out, right? So this is 300 by 16. Similarly, temperature of SO2 by molar mass of SO2. So temperature of SO2 is 927. Please don't forget to convert it to Kelvin. It will be 1200, right? and the molar mass of sulfur dioxide, that is 64. So actually that is 1:1. So this will be the correct answer. So questions like these are very, very common in JEE, right, based on the molecular speeds. Moving to the next question. This question is not only based on the molecular speeds but also on the Maxwell-Boltzmann distribution. Okay, so what is this Maxwell-Boltzmann distribution? Actually, it tells you the distribution of the speed or the energy of the particles at a given temperature for a given sample of gas, right? So what do we actually take here? On y-axis we take the fraction of molecules. On y-axis we take the fraction of molecules, particles. Here you can either take speed or kinetic energy, right? Okay, now at a given temperature the graph looks like this. If you increase the temperature, graph becomes like this. If you further increase the temperature, graph flattens out like that. Okay, so please remember that the total area under this Maxwell-Boltzmann graph, it is related to the total number of particles. So for a given gas at a given temperature, in fact for a given sample of gas, the area under the curve will always remain constant. For example, let us say if I have drawn this graph for hydrogen gas, okay, for 1 mole of hydrogen gas, then the area of all these 3 graphs will be same, right, no matter what the temperature, because that is related to the total number of particles. All right, the peak of the graph, you can guess that the peak of the graph corresponds to the maximum fraction of molecules. So by definition this value is the most probable speed. Similarly, this value is the most probable speed, right, and this value is the most probable speed. All right, now these 3 graphs I have drawn for the same gas, let's say, but at different temperature. So please remember, as the temperature is increased, the average kinetic energy of the particles increases, right, because we know that average kinetic energy is 3/2 RT, that is, it is proportional to absolute temperature. So as you increase the temperature, curve flattens out, the kinetic energy increases, right? Okay, similarly, because most probable speed is under root 2 RT by m, right? So with increase in temperature, the most probable speed also increases. So as you increase temperature, you can see the most probable speed is also increasing. Now let us come back to the question. I think basics are enough. So here in this question, what is what they have asked? So points 1, 2 and 3 in the following plot respectively correspond to. So this is the most probable speed 1, this is 2 and this is 3. You can clearly see that the most probable speed of case third, it is greater than that of case 2, which is greater than that of case 1, right? Obviously that means this most probable speed is highest, because on x-axis we have taken speed, this is less and first is least. Okay, now most probable speed is under root 2 RT by m. Again 2r is constant, right? Square root is in all of them. That means you just have to compare the ratio of temperature and molar mass. Did you guys get my point? Right? Here we have to compare the most probable speeds of 3 different gases at different temperatures, right? So constants will not matter because we are actually comparing them. So 2r will cancel, square root will cancel, because greater the number, right, greater will be the square root here. So T by m is just what we will compare, right? Now for hydrogen, temperature is 300 and molar mass is 2, right? Again I'll use molar mass in gram because we are comparing. So this is 150, obviously. So the value of T by m for hydrogen gas, it is 150. So of course hydrogen has to have one of the highest speeds because of the least molar mass. Now for nitrogen, temperature is 300 and molar mass is 28, and for oxygen temperature is 400, molar mass is 32, right? How to compare them? We don't have to calculate exactly. I can write this as 100 by 8. Am I correct? Yes, so I can write this as 100 by 8. Let us also convert to 100 by something. So if I divide it by 3, so this is this 100 divided by 9.3. So this is 100 by 9.3, this is 100 by 8. So of course this fraction is larger, right? Because this denominator is bigger, fraction is smaller, so this is larger. So second value is for oxygen. right? Okay, second value जो है is for oxygen. So now you can compare what will be the correct answer, right? Okay, and the least value 100 by 9.3, because this denominator is large, fraction should be small, so the smallest value of most probable speed, that will be for nitrogen. Okay, then moving to this question. This question is based on one of the most commonly used expressions in thermodynamics. The combustion of benzene liquid gives carbon dioxide and water, given that the heat of combustion at constant volume. So do you guys remember that heat of combustion, or in fact heat at constant volume, it is nothing but change in internal energy, right? QV is change in internal energy, and heat of combustion at constant pressure. What is heat transferred at constant pressure? That is delta H. So given that the heat of combustion at constant volume, so this is given to be delta U. This is given to be delta U, and the question is, what is the heat of combustion at constant pressure? That is, what is delta H? Now what is the relation between delta H and delta U? Enthalpy and internal energy. So this is one of the most commonly used expressions, as I said. So do you guys remember, this is the expression H is equal to U plus PV, right? Okay, now from this we can derive many expression. For example, delta H is delta U, right? We can derive this V delta P if the process is isochoric, right? Because actually you can write this as delta H is equal to delta U plus V delta P and P delta V, right? So if the process is isochoric, delta V will be 0, so it will be V delta P for isochoric process. Am I correct or not, right? So if the process is isobaric, then delta P will be 0. So now it can be written as delta H is delta U plus P delta V. So this you can write for isobaric process. Alright, okay. Then if you substitute PV by RT, then for 1 mole ideal gas, you can also write delta H is delta U plus R delta T. This is also another expression that we use. Or in case of chemical reactions, we also use delta H is delta U plus delta Ng RT, which is what we will use in this question, right? So this is again very commonly asked expression, right? Delta H is delta U plus delta Ng RT. Here, in such cases, first you'll have to write the combustion equation or whatever equation they have given, right? So benzene is liquid, C6H6 liquid. Combustion means reaction with oxygen, gaseous oxygen. They have indicated that CO2 is gas and H2 is liquid here. So of course, by looking at benzene, we can say we will get 6 CO2 gas, and by 6 hydrogen we will get 3 H2O liquid. Is that clear? Right? So 6 CO2 and 3 H2O. Now how many oxygens will we require? So 6 into 12 plus 3, 15. That is, we will require 15 by 2 oxygen molecule. Now let us calculate delta Ng in this case, right? Delta Ng is gaseous moles of products, which is 6, right? Gaseous moles of products, which is 6. Water will not be counted as it is a liquid, minus gaseous moles of reactants. This is liquid, will not be counted. So this is 15 by 2. Is that clear? Is that clear? So this will be 6 into 12 minus 15, that is minus 3 by 2. So this is delta Ng. That is how we calculate delta Ng. Please remember, it is used in equilibrium also, you know, right? The relation between Kp and Kc. So delta Ng is minus 3 by 2. Now we will use the expression which we derived, right? So delta H is something we have to calculate. Am I correct? Heat of combustion at constant pressure. Delta U is given, which is minus 3263.9 kilojoule per mole, right? Now you have to very carefully substitute the value of delta Ng RT. That is again where some students make mistakes. So delta Ng is minus 3 by 2, right? The value of R, it is given 8.314, and temperature is given is 25 degrees Celsius, right? Temperature is given 25 degrees Celsius, so this is 298. Now this will be in joule because you have substituted the value of R in joule, 8.314, right? So you have to divide it by 1000 to convert it into kilojoule because your delta U is in kilojoule. Is that clear, right? So this is approximately 115 to 450 and something like 4 kilojoules. So I think the answer should be, and because it is minus sign, so it will be minus 3 to 4 point something. So I think this will be the correct answer. You can calculate, right? So that is the kind of question you get on this. So here minus 3 to 67.6 kilojoule per mole will be the correct answer, right? Moving to the next question. Questions based on entropy, work done, heat transfer, they are also very common. You guys know that, right? So read this question carefully. 1 mole of an ideal gas at 300 Kelvin in thermal contact with the surrounding. So process is isothermal. If the system is in thermal contact, so heat is being continuously transmitted so that the system stays at the same temperature as the surrounding. So the process is isothermal here. Now the gas is expanding from 1 liter to 2 liter at a constant pressure of 3 atm. So please remember, whenever the pressure is constant, right, whenever the external pressure is constant, the process is irreversible. The process is irreversible, the pressure is constant, right? So now we can calculate what is the work done, minus P delta V, right? This is an expression we use very commonly. So work done is minus P delta V, right? Okay. JEE is so kind, they have given the value of liter atm also. Otherwise, please remember 1 liter atm is 101.3 joule. So minus, what is the pressure? 3 atm, right? Delta V is 2 liter minus 1 liter. Okay, delta V, the gas is expanding from 1 liter to 2 liter. So delta V is final minus initial 2 minus 1. So this is minus 3.0 liter atm, or minus 3.0 multiplied by 101.3 joule. Is that clear? Is that clear, everyone, right? Okay, now the twist comes. This is not just the answer, because they have done a little bit of, confusion created. Confusion they have tried to create. So 1 mole of an ideal gas at 300 Kelvin and isothermally. So you guys remember from the first law of thermodynamics, delta U is Q plus W, right? If the process is isothermal, delta U will be 0, right? Because the internal energy of a gas, it is a function of temperature, right? If temperature is constant, internal energy will be constant. So from the first law of thermodynamics, Q will be negative of W, right? For an isothermal process of an ideal gas, please remember heat transferred is negative of the work done. So if work done is minus 3 into 101.3, heat transferred by the system will be plus 3.0 into 101.3, right? So heat transferred by the system is 3 multiplied by 101.3. Now they have asked the change in the entropy of surroundings. So we know that the entropy of surrounding is obviously enthalpy of surrounding divided by temperature of surrounding, right? A very simple question. Entropy is heat transferred divided by temperature, so enthalpy of transfer or heat of transfer. Now please remember that what is the relation between the heat transferred by the system and the surrounding? Obviously they are related as negative of each other. If a system releases 40 kilojoule of heat, surrounding must absorb 40 kilojoule of heat, right, by the conservation of energy. So if system releases 40 kilojoule of heat, for the system Q is minus 40. Where did this heat go? Surroundings absorbed it. So for the surrounding, Q is plus 40. What I am trying to say, if Q for the system is plus 3, Q for the surroundings, it will be again minus 3 into 101.3 joule. Is that clear? Alright. Now finally the entropy change is enthalpy or heat transfer divided by temperature. So just substitute the value. Delta H would be minus 3 into 101.3 joule divided by the temperature, which is given to be 300. So I think it will be minus 1.013, right? So the correct answer would be the entropy change of the surrounding will be minus 1.013. So that will be the correct answer. Okay. So some important concepts we have learned, that constant pressure means irreversible. Work done is minus P delta V. Then remember the factor, conversion factor. Then for isothermal process of an ideal gas, Q is equal to minus W, and entropy change is heat divided by temperature, and heat of the surrounding is negative of the heat of system. So many concepts in one single question. Okay. Moving to the next question here. So please revise the types of enthalpies in thermodynamics very carefully. You guys are aware there are a lot of enthalpy types: lattice enthalpy, bond enthalpy, enthalpy of formation, which is very important, right? Then we have ionization, electron gain, hydration, different types of enthalpies are there. So how do we define a standard enthalpy of formation? So a standard enthalpy of formation is defined that only 1 mole substance should be formed. Only 1 mole substance should be formed, and it should be formed from its reactants, right? Now the reactants must be elements. Reactants must be elements in their stable state. Reactants must be the elements in their stable states, right? So how do we define the standard enthalpy of formation? Only 1 mole of the substance should be formed. That substance should be formed from its elements, right? Reactant should not have any compounds. Okay. For example, CO plus half O2 gives CO2. The enthalpy change of this question does not qualify as the enthalpy of formation, because carbon monoxide is not an element, it's a compound, right? So let us see what is the problem here. The element should be in their most stable states, right? So C2H6, 1 mole gas is forming, that's perfect. 3 hydrogen gas is perfect, but carbon gas is not good, because we know the stable form of carbon is graphite, solid graphite. So this cannot be the correct answer. Here 2H2 gas is okay, O2 gas is okay, but 2 moles of water cannot be formed, right? So again that is not allowed. 1 mole of ozone is formed. It is formed from the stable form oxygen, right? And 3/2 both are gases, so this is the correct answer. And here 1 mole of sulfur dioxide is formed. It is formed from S8. We will assume it is rhombic sulfur, which is the reference state, and oxygen gas. So options C and D, they are the correct answer. This question is from advanced, so there are multiple correct answers here, okay, right? Then this question, these kind of question are again common, right? Now where you are given some enthalpy changes and some you are supposed to find out, okay? Now please remember, here you use Hess's law, but there are some special cases where we can do the directly, where we can calculate the enthalpy change directly from the given data. I will discuss that in next question, but this question we will do by the application of Hess's law, right? I'll give you some time to go through the question. It is not really very difficult, just a little bit of calculation it has. So carbon graphite plus oxygen gives CO2, all right. Then H2 gas plus half O2 gives H2O. Carbon dioxide gas plus 2H2O gives CH4 plus 2O2. So you can see first equation is the enthalpy of formation of CO2. Next equation is the enthalpy of formation of water. But this equation is what? It is just a normal reaction, right? It is the opposite of combustion enthalpy of methane, right? So it's a mixture of combustion and formation. We cannot do this question directly. So we will apply Hess's law. Now I will tell you a short way to apply Hess's law. So the value of enthalpy change for this reaction is what they have asked, right? That is carbon as graphite plus 2 hydrogen gas produces CH4 gas. Let us pick the species one by one. Let us first pick carbon graphite. It is in this which equation? First one, right? So I need carbon graphite on the reactant side. Yes, reactant side. I need 1 mole. Yes, 1 mole. So I will pick the first reaction as it is, right? So first reaction as it is. So carbon graphite plus oxygen giving CO2. So enthalpy change will also come as it is. So minus 393.5 kilojoule. All right. So that is enthalpy change. Next I need hydrogen. Where do I have hydrogen? In the second equation. But is it okay? No. I need 2 moles of hydrogen. Here it has only 1 mole of hydrogen. So I will multiply this equation by 2, right? I'll multiply it by 2, okay? When you do so, the enthalpy change will also be multiplied by 2, okay? Please remember, whenever you multiply your equation, enthalpy change also gets multiplied by the same number. So I'll multiply this by 2, so 2H2, so that will be O2, and that will be 2H2O, right? So enthalpy change will be minus 2 multiplied by 285.8, right? So minus 393.5 minus 2 into 285.8, okay? Lastly, I need methane gas. Here, yes, they have one methane gas. I will pick the equation as it is, right? So CO2 plus 2 water, it gives methane and 2 oxygen. Because you have picked the equation as it is, enthalpy change will also be picked up as it is. So 890.3. Now we have formed our entire equation, but for your own satisfaction, you can try to add these. Okay, so CO2 will cancel, and here 2 water will cancel, right? And 2 oxygen will cancel. What you will be left with is carbon graphite plus 2 hydrogen, right? And methane. Yes, this is precisely what we needed, right? This is precisely what we needed. So now you can do very easy the enthalpy change of this reaction. The enthalpy change of this reaction will also be the sum of these, right? So this is minus 393.5 plus 2 multiplied by minus 285.8 and then plus 890.3. Is that clear? Is that clear? So now I think you can solve this. 57, 570, and then 5, 6, 7, 8, 870, and then it will be a little bit of negative answer, not very much. So I think that will be the correct answer. You can solve it, right? Option C will be the correct answer, minus 74.8 kilojoule per mole, right? Now these are the kind of question which I was talking about. You can do directly. Read the question very carefully. The standard enthalpy of formation of CO2, water and glucose, they are given, and they've asked what is the standard enthalpy of combustion per gram of glucose. Okay, so read the question again. They have given you the enthalpies of formation and they've asked is the enthalpy of combustion. Okay, so now I will tell you a trick using which you can bypass Hess's law a lot of times. So please remember that if combustion enthalpies are given or bond enthalpies are given, please mind or, not and. You cannot have a mixture of these, right? So if combustion enthalpies are given and bond enthalpies are given, okay, then in that case the enthalpy change of a reaction is very simply the enthalpies of reactants, the combustion or bond enthalpies of reactants minus the enthalpies of products, right? So if you are given the combustion enthalpies or the bond enthalpies of different reactants and products, then you can calculate the enthalpy change of your reaction, whatever the equation is, the enthalpy change of that reaction as the total enthalpies of reactant minus total enthalpies of products. But if you are given enthalpies of formation, right, then you do the reverse. If enthalpy of formation are given, then you do the reverse, as in that case the enthalpy of reaction would be the summation of enthalpies of formation of products, right, minus the enthalpy of formation of reactants. Right, enthalpy of formation of reactants. We will apply the second formula here. The question is the standard enthalpy of combustion of glucose. So let us first write the combustion of glucose. So that will be C6H12O6, right, plus oxygen. Of course it will give you 6 carbon dioxide and 6 water molecules. Am I right? So C6H12O6, that is the formula of glucose. So it will give you 6 CO2 and 6 water molecules. Now 6 oxygen are there already, so I'll need 6 oxygen here. Okay, that doesn't matter anyway because the enthalpy of formation of oxygen will be 0. Please remember that for elements in their stable form, the enthalpy of formation is 0. Now, what will be the enthalpy of this reaction? Okay, so please note that you do not look at the value that you have to calculate, you look at the value that you are given. So standard enthalpy of formation are given. So when formation enthalpies are given, we do products minus reactants. Okay, so what I'm going to do here, products minus reactants. So of course 6 multiplied by the value of CO2 is minus 400, right? Then plus 6 multiplied by water. The value of water is minus 300 minus glucose, right? So products minus reactant, that is what we have to do. So glucose, that is given to be minus 1300 and oxygen will be 0. Is that clear, right? So because it is combustion enthalpy, it has to come out to be negative. Remember something, okay, right? Because they have asked the standard enthalpy of combustion per gram of glucose. So combustion is exothermic. These cannot be the answers, right? So this will be minus 2400 minus 1800 and this will be plus 1300. Is that clear? Okay. So now this will be minus 500. So minus 2900 kilojoule is what you will get. But be careful, this is not the answer. Because whenever you calculate enthalpies in reaction, they are always molar values, right? They are intensive, they are molar values. They have asked the enthalpy of combustion per gram. So we will divide it by the molar mass of the glucose, right? So 2900 kilojoule divided by 180. So there is no doubt about it. The answer will come out to be minus 16.11. Okay. So that is how you solve such type of questions. Now moving to the next question. Again a formula on which questions are asked in JEE. Please remember the relation between Kp and Kc, it is this, right? Kp is equal to Kc RT raised to the power delta Ng. Kp is equilibrium constant in terms of partial pressures for gases and Kc is the equilibrium constant in terms of concentration, right? The value of R usually we take it to be 0.08206 liter atm by Kelvin mole. Temperature has to be in Kelvin and delta Ng, you remember the gaseous moles of products minus gaseous moles of reactants. There are only two cases when Kp is equal to Kc, right? Of course Kp will be Kc when this term is 1. This term is 1 when the power is 0, right? So Kp is equal to Kc when delta Ng is 0. That is either there are no gases or the gaseous moles are equal. Let us look here. So let us calculate the value of delta Ng in all the four cases. So here the value of delta Ng would be the gaseous moles of products, which is 2, minus reactants, which is 1. So delta Ng is 1. Here delta Ng is 2 moles of gases on the product side, 2 moles of gases on the reactant side. So that is 0. Here also 2 moles on the product side, 2 moles on the reactant side. So again 0. And here again 2 moles of gases on the product side, 2 on the reactant side. So 0. So this is only one case where the delta Ng is not 0, it is 1. So if delta Ng is 1, Kp is Kc multiplied by RT, which clearly means that Kp is not equal to Kc. So that makes option 1 our correct answer. Let us come back here. Kp is equal to Kc. First when delta Ng is 0. Second when temperature is 1 upon R, right? Because if temperature is 1 upon R, so R into 1 upon R will cancel out 1 raised to the power, anything is 1. So 1 upon R is approximately 12 Kelvin, right? At this temperature is also Kp equal to Kc. Then another type of question like this, they are also very common in JEE Main, right? You are given the equilibrium constants of some equation and you have to relate them. We do them similar to the question we discussed in thermodynamics. The only difference is now you have to remember the rules, how equilibrium constant gets modified as you modify an equation. For example, this is 6ab and this is 2ab. So by looking at these two equations, you can figure out that I have to make this equation equal to this. And how can I do that? First I will reverse this equation, right? First I'll reverse this equation. So this will become 2ab given a2 plus b2. Now please remember, when you reverse the first equation, right, when you reverse the first equation, the equilibrium constant gets reciprocal, right? Okay, so I'll not change the symbol for the equilibrium constant, but if this is k1, then this will be 1 upon k1. Am I correct? Right? So when you reverse this equation, 2ab gives a2 plus b2. So you have reversed the equation. So please remember, whenever you reverse the equation, kc becomes reciprocal. So this will become 1 upon k1. Now this is 2ab and this is 6ab. That means I'll have to multiply this equation by 3. So that will give me 6ab and 3a2 and 3b2. Now when you multiply this equation by 3, the equilibrium constant, whatever it is, it also becomes the cube, right? Whenever you multiply your equation by any number, so kc becomes the power of that number. Okay, so this is 1 upon k1 cube. Now please see, this equation is nothing but this equation, that is, this is equal to k2. So k2 is k1 raised to the power, right, inverse cube. So this is k2 is equal to k1 raised to the power minus 3. That is the correct answer here. Then this question, a good example to revise the relationship between the reaction quotient and equilibrium constant, and the equilibrium constant and the standard Gibbs energy, right? So how will you do this question? You can pause the video, solve the question yourself and check the answer again. If you're not sure of the concept, then you should watch the solution, right? So the standard Gibbs energy change at 300 Kelvin for the reaction 2A gives B plus C is 2494.2 joule. The standard Gibbs energy delta G naught is given. At a given time, the composition of the different substances is also given. And the question is, the reaction proceeds in which direction? So we know that we can tell if QC is equal to KC, reaction is already at equilibrium. If QC is less than KC, then reaction will occur in the forward direction. If QC is greater than KC, reaction will occur in the backward direction, right, reverse direction. But for that, we should know both QC and KC, none of which is given. QC we can calculate directly. QC is expressed in the same way as KC, right, because KC is in fact a special case of QC, right? You guys know that the ratio of products and reactant concentrations, it becomes equal to Kc when the reaction reaches equilibrium. So please remember, Kc is a special case of Qc only. So Qc is Bc divided by A square, right? So reaction quotient is concentration of B into C divided by A square. The concentration of B is 2, C is half and A is 1 upon 2 square. So this will be equal to 4, right? So Qc is 4. Now I just have to find out K and compare it with the QC, right? Now you guys know that delta G naught is, delta G is delta G naught plus RT ln QC. This is a formula we use a lot of times in the derivation of Nernst equation also, for example. Now please remember that at equilibrium delta G becomes 0. At equilibrium delta G becomes 0 and QC becomes Kc. So the relationship between delta G naught is minus RT ln Kc, the relationship between the standard Gibbs energy and the equilibrium constant. Now delta G naught value is given 2494.2, temperature is given 300 Kelvin, right? The value of R is given. Let us see what do we get. So this is minus 2494.2 joule, right? It is in joule only. R is 8.314, right? Temperature is 300 ln Kc. So I think Gibbs energy is 2494.2, the standard Gibbs energy plus 2494.2. So this is positive, right? Now I think if you will solve it, so you will get this only, right? Yes, right? So you will get this only. So this will cancel, right? And you will get ln Kc as minus 1. Ln Kc as minus 1. So Kc will be e raised to the power minus 1, right? Because it is natural log, okay? Log to the base e. So this is 1 upon, the value of Ec is 2.7 approximately, also given here. So of course Kc is less than 1. You don't have to solve it, right? So ln Kc is minus 1, Kc is e raised to a minus 1, which is 1 upon 2.7. That is, your equilibrium constant is less than 1, whereas Qc is 4. So clearly this is a case of QC greater than K, right? So when this happens, reaction occurs in the reverse direction, backward direction. So reverse direction because Q is greater than K. So very good example of the direction of reaction, that's relation between standard Gibbs energy and equilibrium constant. This is. Then this is a very good question based on the solubility product constant and the common ion effect and also of pH, right? Try this question. The molar solubility of cadmium hydroxide is given. It might be molar, if not then we'll for dilute solutions anyway we can assume molality is equal to molarity. The expected solubility of this salt in a buffer solution of pH 12. Okay, so if you are using cadmium hydroxide in a buffer solution of pH 12, so do you guys remember pH plus pUH is 14, right, at 298 Kelvin? We can say that for any aqueous solution at 298 Kelvin, sum of pH and pUH is 14. So if pH is 12, then obviously pUH is 2, right? If pH is 12, then obviously pUH is 2. Now pUH is minus log hydroxide ion concentration. So log hydroxide is minus 2, and if log x is y, then x is equal to 10 raised to the power y. So hydroxide ion concentration will be 10 raised to the power minus 2 molar. Okay, so this is a good way of directly indirectly giving the hydroxide ion concentration. So pH is 12, pUH is 2, and hydroxide ion concentration is 10 raised to the power minus 2. Now cadmium hydroxide molar solubility is given, okay, and we have to find out the solubility in a solution which contains 10 raised to the power minus 2 molar of hydroxide. So first thing that we will do, we will find out the KSP. Okay, there is one cation, there is two anion, so 1 raised to the power 1, 2 raised to the power 2, solubility raised to the power 1 plus 2, right? That is how we write KSP for a salt which has some cation, some anion, then number of cation raised to the power number of cations, similarly for anions, and then this, okay. So KSP will be 4 1.85 into 10 raised to the power minus 5 into 3. This is your KSP, okay, right? Now molar solubility was given, we calculated KSP. pH was given, we calculated hydroxide ion concentration. Now the final step, we have to calculate the solubility of cadmium hydroxide. Let us do this. So cadmium hydroxide, when it dissolves, it produces one cadmium ion, of course, right, and two hydroxide ions. Am I correct? Right? Now this solution already contains 10 raised to the power minus 2 molar of hydroxide, right? Now let us suppose in this buffer solution the solubility of cadmium hydroxide is capital S moles per liter. So the concentration of cadmium will be S, the concentration of hydroxide will be 2S, right? 1 mole gives 1 mole of this and 2 mole of this, so S and 2S. Now let us write the KSP. KSP will be the concentration of cadmium, which is S, the concentration of hydroxide, which is 2S plus 10 raised to the power minus 2. This is equal to that value, right? 4 into 1.84 cube, you will have to work it out, 10 raised to the power minus 15, I think it is, yes, okay. Now in these cases you can see the solubility is very small, the solubility product is very small. So in comparison to the concentration of this common ion, we will ignore this, right? Right, because you can see the solubility is very low, 10 to the minus 5, but this concentration, this number is almost 1000 times larger, right? So, so what happens here? So S into 10 raised to the power minus 2, and because there is a coefficient 2, so we will put it square, right? So this will be 10 to the minus 2 square is this number, so I think now we can solve it. So this is 4 into 1.84 cube, 10 to the minus 4 plus 4 minus 11, right? So you can solve it, 1.8 into 10 to the power 20, you will get this as the correct answer, right? 2.49 into 10 to the minus 10 molar, right? That will be the molar solubility. So that is how you do question based on solubility product, common ion effect, and pH. So very good example based on that. This question I selected because it is based on hydrolysis. Again, on hydrolysis, there are very often questions in JEE. Salt hydrolysis, we know that salts can be of 4 types. Those come from strong acid and strong base, or weak acid and strong base, or strong acid and weak base, or weak acid and weak base. Can you tell me what kind of salt is this? Sodium salt of benzoic acid, substituted benzoic acid. So benzoic acid is a weak acid. We will assume it is a weak acid, right? The value of dissociation constant also tells so. So please remember that if a salt comes from weak acid and a strong base, right, then what happens? The anion of the salt, A minus, it reacts with water, right? Because it has come from weak acid, it's a strong conjugate base. It takes H plus from water and it produces hydroxide, which means the pH of the solution will be above 7. So please remember, whenever you dissolve a salt of weak acid in strong base, the pH will be above 7, right? So what will be the formula? Derivation we will not go into, because at this stage you should remember the formulas. So this will be 7 plus half pKa of the weak acid plus log of the concentration of the conjugate base, right? C is the concentration of the conjugate base. Now let us do this question. We have to find out the answer also. So you can see, guys, the dissociation constant is 10 to the minus 4. So pK will be 4, right? Because pKa is minus log Ka, right? Log 10 raised to the power x is x. So this will be 4, right? So this will be 7 plus half 4 plus log of, what is the concentration? The pH of 0.01 molar of solution of its sodium salt. The concentration of benzoate, substituted benzoate, will be 0.01. That is 10 raised to the power minus 2. Okay, so again 7 plus half 4 log 10 raised to the minus 2 will be minus 2, right? Log 10 raised to the power x is x. So this will be 2 by 2 is 1, 7 plus 1, 8. So the pH of this solution will be 8. As expected, it is greater than 7. Okay. Now please remember, if the salt comes from weak base and a strong acid, then what is the formula of pH? Now the pH will be less than 7. So it will be 7 minus half pKb, because the salt comes from weak base. So 7 minus half pKb plus log C. That will be the pH. And finally, if the salt comes from both weak acid and weak base, then guys, what is the formula? Then pH will be 7 plus half pKa minus pKb. That will be the formula then. Alright. Moving to the next question. When equal volumes of the following solutions are mixed, precipitation of AgCl. So this question I took because whenever I discuss this question in the class, almost everybody makes a mistake, right? And these kinds of questions, they do come in JEE. So what you have to do here is that this case is similar to the QC and KC, right? Here K is KSP, the solubility product constant of the salt, and Q is replaced by KIP, which we call ionic product. Okay, so for AgCl, ionic product is simply the concentration of silver ion and the concentration of chloride ion, right? Now what we will do, we will find out KIP from the given data, compare it with KSP. Okay, if KIP is less than KSP, reaction occurs in the forward direction, that is salt dissolves. If KIP is greater than KSP, then reaction occurs in the backward direction, that is silver and chloride ions come out of the aqueous phase as salt, that is precipitation occurs. So basically, please remember, for precipitation, your ionic product must be greater than your solubility product constant. Is that okay? For example, I'll take the second option, let's say. Okay, so KIP would be, now the concentration of silver is 10 to the minus 5 molar, concentration of chloride is 10 to the minus 5 molar. But that was when they were not mixed. When you mix equal volume, 1 liter of, let's say, silver, 1 liter of chloride, total volume is 2 liters. right? Total volume is 2 liters. So volume has doubled from 1 to 2 liter, concentration will become half, right? So silver concentration, actually it is this, and chloride concentration also, that will be this, okay? So this is 1 by 4 or 0.25 into 10 raised to the power minus 10, okay? That will be 0.25 into 10 to the minus 10. So that will not be the correct answer because the KSP is 1.8 into 10 to the minus 10. So KIP is less than KSP. In second case, precipitation will not occur, right? So I think precipitation occur in the first step, because there it will be 10 to the minus 4 by 2, 10 to the minus 4 by 2, 0.25 into 10 to the minus 8 or 2.5 into 10 to the minus 9. Yes, in the first case guys, please do that yourself, right? Strengthen your concept. It will, so KIP will be greater than KSP and precipitation will occur. Then this question based on buffer, right? We cannot skip buffer. So here, how do we identify that buffer is formed? Very easy. Buffers are of two types, acidic and basic, right? Buffers are of two types, acidic and basic buffer, right? Acidic buffer and basic buffer, right? Now what happens in acidic buffer? You have a weak acid, HA, and its conjugate base. Both species should be present, right? A weak acid and its conjugate base. Similarly, in basic buffer, you should have a weak base and its conjugate acid, both, right? Now, what are the equations to find out the pH of the acidic and basic buffer? Here, the pH will be pKa of the acid plus log concentration of the conjugate base, whatever it is, divided by the concentration of acid. Alright. In a basic buffer, if you use the same form of the equation, which you should because it is easier to remember. So here the PUH is what you will get, will be equal to pKb because we are discussing basic buffer, plus log, here you used conjugate base, now you will use conjugate acid, divided by the concentration of base. Alright. So that is how you calculate the pH of acidic and basic buffer. Of course, you can use pH plus PUH is 14 to calculate the pH. Now, what do we have to do in this question? So CH3NH2 is the weak base, right? It is the weak base WB. It reacts with HCl, H plus of HCl, and it gives you CH3NH3 plus, right? Which is the conjugate acid, right? So that is the weak base and that is the conjugate acid. Now this methylamine is 0.1 mole and H plus is 0.08 mole. You can use the concept of limiting region, not rocket science, it's very simple here. So 0.1 mole of the base and 0.08 mole of the acid. So H plus is the limiting reagent, right? So out of 0.1, 0.08 mole will convert to that side and 0.02 mole will remain. That means in the mixture you have 0.02 mole of the base and 0.08 mole of the conjugate acid. Yes, this is a basic buffer solution. Alright. Now please remember that for any base, BUH gives B plus and OH minus, we can always write the base dissociation constant is B plus OH minus divided by BUH, right? We can always write this. We can always write this Kb is B plus OH minus by BUH. So Kb is given for methylamine, that is 5 into 10 raised to the power minus 4, right? The concentration of conjugate acid is 0.08 because they are in 1 liter. So, you know, number of moles is molarity, right? Then hydroxide ion concentration divided by the concentration of base, whatever it is. So that is 0.02. So this will cancel as 4 and the concentration of hydroxide will be 5 by 4 into 10 raised to the power minus 4. Now you guys know at 298 Kelvin the H plus and OH minus ion concentration is what? At 298 Kelvin H plus and OH minus ion concentration is 10 raised to minus 14, right? The question is, what is the resulting H plus ion concentration? So H plus ion concentration is 10 raised to the power minus 14 divided by hydroxide, which is 5 by 4 into 10 raised to the minus 4, right? So this is 0.8 into 10 raised to the power minus 10, or 8 into 10 raised to the power minus 11. So that is the answer that you will get. So that is how you have to apply the buffer equations, right? And that is how you have to, if they are asking the concentration of H plus and OH minus, please prefer to use this expression, okay? If they are asking about pH and pUH, then use these expressions. All right, so that's all in this power up series. Guys, I hope you benefited. Please subscribe to this YouTube channel, press the bell icon so that you get notification for the next session of all the subjects. So I'll return again here with the remaining chapters of physical chemistry, which will help you in your preparation. So wish you all the best. Take care. Bye bye. हाँ कितनी देर का हुआ?